This is Shoival Gupta welcoming you to the second lecture on tectonics and geodynamics, part of this NPTEL course. In the last lecture, we talked about the origin of about the differences between the continents and the oceans. We've seen that they are different entities, and on the surface of the earth, the continents and the oceans form very different things. So they are compositionally different, they are different in thickness, the elevation is different, right? And the ages are also different. So all of these are observations. These are things, these are indisputable. These are things that we can see. The question is, we are trying to evolve a theory in this course which can actually explain these observations. So the first part of it was actually explaining that the continents did not always look on the surface of the earth, they didn't always look the way they are today. So they had changed in the past. In other words, the continents have been moving around on the surface of the earth. This theory is what is called continental drift theory, and today we will be talking about the origin of that particular theory and finally the demise of that theory as well. So that's why lecture 2 I've called it the demise of the theory, because that is what it will ultimately end in. Now the concept that we will talk about here is the beginning and the end of the continental drift theory. So the continental drift theory is the theory that talks about this movement of the continents on the surface of the earth. Now, let's just go back to this, a flashback into the last lecture. And this is that world map which we have used in the past. So you have North America, South America, Europe and Asia, Africa, Australia, and our little country India is here. I call it little, it's actually big, but it's little when you compare it with the land masses around it. Now, as we said, right, we had noticed this similarity. This is what we had started off with, right? The similarities between the eastern coast of South America and the western coast of Africa, right? And this is what actually gave rise to the thought that the eastern western coast, because they were so similar, right, they match across the Atlantic Ocean, so were they once together? So this was an idea that had already been considered, right, as early as the 17th century, and it continued up to the end of the 19th century. Now we move into the 20th century, and as we move in, right, we again need to understand what we are talking about with respect to the crust, the ocean and the continental crust. So the continents and oceans, as I told you, are fundamentally different. I talked about the differences a while earlier. The thing is, the continent itself is divided into two parts. Now I've shown, this is actually more schematic. If I make it even simpler, you can actually think of something like this. So you can actually think of the continents being of two parts, the upper part being the lighter part composed dominantly of silicon and aluminium. This would be the Sial, right, as it's shown here, and this part is the sematic part. This part is the Sima. Pardon me. This part is the Sima, which probably is similar in composition to much of the oceanic crust. So the continents that we are living on, right, so we can actually be considered to be living out here, right? So that's where we are. We are living on the Sial. And so this Sial is actually placed on top of the Sima, and the Sima continues underwater. So if I want to draw ocean water, so this is the oceans. So that's my very poor diagram trying to tell you what we're talking about. So the idea is that the continents grossly, right, have an upper part and a lower part, and they're actually separated by what we now call the Conrad discontinuity. Okay, so now the base of the crust, by the way, is the Mohorovicic discontinuity separating the crust from the mantle. So I must emphasize at this point that these early arguments that people were talking about continental drift, the Moho did not enter into the argument at all, right? So we were just talking of the continents with respect to the oceans and how the continents moved with respect to the oceans. That was the whole idea of continental drift. Now, the birth of the continental drift theory, right? Following all of this that we discussed in the last lecture, right? All the people whose concepts we talked about, this is largely credited to two people, right? And remarkably, they found both of these theories completely independently of each other and in two completely different continents. In fact, they were the two continents that were believed to have been joined, so North America and Europe. So 1908, Taylor, right, formulated his theory or proposed his theory of continental drift in the USA. 1910 was the first time that Alfred Wegener, and in fact his early theory was the first proposition was recorded in German. He gave a lecture in German in somewhere in Germany, right, and that was also in 1908, but it was published, I believe, in 1910. So completely independently of each other and remarkably almost simultaneously, the theory of continental drift was proposed by these two enormously gifted geniuses. Now, when we talk about continental drift, let's talk about each one independently because they formulated the ideas independently. Now, Taylor's idea of continental drift was that you had huge landslides. The continents initially were not located where they are today. The continents formed two different land masses. One was near the North Pole, right, and the other was near the South Pole. And all of these continents were later dragged towards the equator. This was Taylor's idea. So all the continents as we see today dispersed around, they actually were in the form of just two land masses, and they were separated by the bulk of the earth in between. So the two poles had the two continents, and there was ocean in between. Now, the part that was near the North Pole, Taylor referred to that as Laurasia, right? And the part that was near the southern continents together, this was referred to as Gondwana land. Now, just out of interest to us in India, the term Gond is derived from a tribe in India, right? And we still have, I've had students who are Gonds, right, who have actually studied geology. I don't know how many of them know that they have given their surname actually to one of the most interesting and remarkable features in geological literature, right, Gondwana land. So the land of the Gondwanas, Gonds really, is now called Gondwana land per se. So the southern continents were together in what forms Gondwana land. This was located near the South Pole at that time. Now, according to Taylor, one of the things that had to be explained were the presence of these mountain belts. Now, these mountain belts are things that have fascinated people for a long time, right? People have tried to explain why mountain belts exist. And what Taylor was trying to propose was that the mountains were formed as these lobes. You had these large continents located near the poles. As they were sliding towards the equator, the drag created these mountains and the frontal parts of these sliding lobes. So the slopes was actually sliding from say the North Pole, they were sliding towards the equator, and as they were going there, right, the mountains, the drag would create these lobes in the frontal part, and you'd actually get mountain belts forming at the frontal parts of the lobes. Now, just as this happens, so as a continent is moving, if it's moving in all directions towards the equator, so while there would be lobes in the frontal part, when you're actually moving away, you'd actually split at the top. So you would get stretching and splitting, what we call rifting today, right, in the rear of the lobes. So Taylor's whole idea, the whole idea of how it happened, was actually not very dissimilar to the way in which we think it happened today or accept it to have happened today. But his idea was then that as it slid from the poles towards the equator, so the northern land masses were sliding from the North Pole towards the equator, the southern land masses would slide from the South Pole towards the equator northwards. So towards the frontal end of each of these lobes, right, you'd get the mountains formed, and in the rear end, you'd get this stretching and splitting, right, and this is why these things will be left over in space. Now, what he was advocating was remarkable. This is something that people didn't really understand, or even the geologists at the time found very difficult to accept. What he was postulating is that the continents had moved for thousands of kilometers, and this is lateral movement. You see, so this part is the key. What continental drift was advocating was a lot of lateral movement. Prior to that, people had talked about vertical movement, and in fact, you might be surprised to know even till the 1950s, even till the 1960s, even beyond the origin of plate tectonics, there was a school of thought which did not accept that there had been large-scale lateral movement, right, on the surface of the earth, right. It was mostly vertical movement, and people talked in terms of what are called endogenous and exogenous processes. So this idea of lateral movement was actually really something revolutionary at the time. People were proposing thousands of kilometers over which large continents were moving on the surface of the earth. Now, whenever you actually move something, right, Newton has told us that if you want to create any kind of motion, you need force. What was this force then? Now, this is where Taylor actually erred in a way. He actually thought that the driving force was the moon itself. Now, in his opinion, the moon first of all became the Earth's satellite in what we call the Cretaceous period. Now, the Cretaceous period ranges from 145 to 66 million years before the present time. So, according to Taylor, the moon became the Earth's satellite for the first time in the Cretaceous period. And when it became the Earth's satellite, the gravitational attraction of the moon is what initiated the drag of the continents from the polar regions, right? Laodicea from the northern part, Gondwanaland from the south, and they moved towards the equator. This was the idea that Taylor had proposed. Now, the problem, of course, that came in with what Taylor was proposing was that it was difficult to explain. How would you explain then the presence of mountains that were older than the Cretaceous? For example, we know that if we're talking about the Cretaceous, he was actually talking mostly about things that he could see in North America. And even in North America, right, there were places like the Appalachians, for example, which people knew were very old. Now, how did they know that they were very old? There was no radiometric dating, or it hadn't been dated by that particular time. Well, the idea was that you saw rocks that contained no fossils, and it was assumed that if you have sedimentary rocks which don't contain fossils, it means they must have formed before the origin of life. So a lot of these mountain belts were actually what we call Precambrian mountains, even in North America. So there were mountains known then that were older than the Cretaceous, and if the moon became the Earth's satellite only in the Cretaceous, how would you explain the origin of the mountains that were older than the Cretaceous? So that was the first problem that he had with Taylor's hypothesis. The second one was a more interesting one, and this is something that actually we don't think of too much nowadays. That's the tidal force of the moon. Now, what was Taylor actually talking about? He said that when the moon became the Earth's satellite, right, in the Cretaceous time, the gravitational attraction of the moon is what caused the movement of the continents. Now, today we know that the gravitational attraction of the moon causes the tides on the Earth. Okay, so we see the tidal effect on the Earth, right, that is caused by the gravitational attraction of the moon. However, the tides, right, if the tidal force was that strong, that it could actually move a large bulk of continents from the northern and southern poles of the Earth towards the equator, then that force would have to be very large. And if that force was so large, then the Earth would have stopped rotating. Now, what does this actually mean? Now, it's easier to conceive if you think rather of the moon and the Earth rather than the Earth and the moon. What effect does the Earth's gravitational field have on the moon? Now, I think most of you know that we can always see only one side of the moon, that we call the near side. And the part that we can't see is called the far side. Now, have you ever thought of why we can see only one side of the moon? It's actually because of the tidal effect caused by the Earth. So what happens is that the moon itself, right, the moon suppose is here and the Earth is here. So these are their centers, right? This is not to scale, obviously. So if you now think of it, what happens, the center, if you join the center of masses, because of the enormous mass of the Earth and its gravitational attraction, so the center of gravity of the moon is actually dragged away from its center of mass. So as a consequence, when the moon tries to rotate, what would happen when the moon tries to rotate? What would happen is that it would be brought back, it would be dragged back into the straight line which is joining the center of masses. As a consequence, the moon is tidally locked. So the term we use nowadays is the moon is tidally locked. So it means that the gravitational attraction of the Earth is so great that it does not allow the moon to rotate. Now, What Taylor was advocating was the tidal effect, the gravitational attraction of the moon, which actually enabled, right, these continents or dragged these continents towards the equator. Now, the problem was that if you calculate the magnitudes of the forces, even roughly, the magnitudes of the forces required to make a huge mass of continent and move it towards the equator, then the magnitude of that force required would have actually tidally locked the Earth. The Earth itself would have stopped rotating in one day, in just one day. So this was why, the mechanism that he was proposing, that really couldn't be defended. And therefore, although Taylor had proposed this theory, right, and there was overwhelming evidence which was supporting the theory, nevertheless, he wasn't actually able to explain why this would have happened. Why did the continents move? What enabled the continents to move? So, we now move on to the other side of the Atlantic. Let's move to what Wegener said. Now, Alfred Wegener, right, in Germany, his idea was different. He did not think of two land masses. Now, remember that Taylor said that there were two land masses, Laurasia and the northern hemisphere, with the northern continents, Gondwana land, and the southern hemisphere, the southern continents. Now, according to Wegener, there was only one supercontinent, and that was called Pangaea. Now, Pangaea was just one supercontinent. All the continents together formed this particular continent. And then what happened is that Pangaea, right, the dispersion was caused primarily by rifting. Pangaea itself, a part of it stretched over the poles, and what happened is that it was dragged towards the equator. So essentially, it was a process of what he called the pole flight, which meant a flight from the poles. So it actually moved, the continents moved from the poles of the Earth, right? They were dragged towards the equator. Now, according to Wegener, now he took geological evidence, right, into consideration to say this. I've told you previously about the presence of these similar coal measures that were actually observed, right, between North America and Europe, which was similar, and they had similar fossils. Now, paleontologists and what we call stratigraphers, right, have told us that if you've got similar plant fossils, they must have existed at more or less similar times. So we're actually talking about simultaneous things which were coeval, similar in time. So if you have coal measures, for example, the plants and fossils that are needed to make up these coal measures, these can only be formed, this kind of vegetation is only conceivable when continents are located near the tropics. So if you have these coal measures in North America and Europe, that means both North America and Europe must have been somewhere in the tropics, somewhere near the equator, right? When these coal deposits were being formed, when they being deposited, this vegetation existed. Now, if you join all the continents in the configuration that Wegener thought they had, you would find South Africa would lie somewhere near the South Pole then. So it was a continuous mass of continent with North America and Europe near the equator and South Africa extending up to the South Pole. Then rifting started, the breakup, right? And as breakup started, Pangaea started to break into little pieces, and there was both a northerly movement from the poles, the parts that were near the poles, and there was a westerly movement. Now, again, Wegener also had this job of explaining why, right? What was the driving force? Why should this happen? Now, Wegener came up with a different driving mechanism, and he referred to the Earth's equatorial bulge. Now, what is the Earth's equatorial bulge? Now, if we think of the Earth, we talk about the Earth as a sphere. Most generally, we talk about the radius, the diameter of the Earth, etc. But in actual fact, the Earth is an oblate spheroid. It's not really a perfect sphere. So what it is that it's a little flattened at the poles compared to the equator. So the equatorial diameter is greater than the diameter if you join the poles. Now, because that is there is a little bit of extra mass near the equator, right? You can think of it this way. So this little bit of extra mass is present near the equator. This is what is referred to as the equatorial bulge. So you have some extra mass of the Earth near the equator. Now, what Wegener was saying was it was the gravitational pull of this equatorial bulge which was responsible for causing the rifting of Pangaea. So he thought that this itself was the driving force. Now, as it sounds, I mean, you can imagine that this itself would also have problems, but there was a huge amount of geological evidence that Wegener came up with. Now, Wegener presented a host of geological evidence, and he was actually supported by another person. Now, the most important evidence that Wegener had referred to this Permo-Carboniferous time. Now, this refers to a time between 350 to 300 million years ago, right? So that is the Carboniferous, and then if you move further into the Permian, right? At that particular time, on a large number of different continents which are now spread out in different parts, you see evidence of glaciation. Now, a lot of this glaciation, this is around 300 million years ago. You see glaciation, for example, we have evidence of glaciation in India in the Talchir belts. Now, this is nowhere near the Himalayas. In the Talchir beds is even south of where I'm speaking from in IIT Kharagpur, right? This is even south of this place. So it's a hot place. It's 45 degrees plus in summer in this place. So that place is a place where we know that there are deposits of rocks which were formed from glaciers. So it means that that particular region was at one time in the past covered with glaciers. Now, the fossils and the same glacial rocks you can see in parts of South America, you can see this in the Antarctic, you can see this in South America. So you have evidence for Permo-Carboniferous glaciation in different continents which are now separated by the oceans. Not just the rocks. We also see that there are correlatable land fossils, correlatable freshwater animals and plants. Now, what is important here is that if you have land animals, obviously that means that the animal must have been able to move from one part to another without having to bother about crossing any body of water. So you can't do this over an ocean. The same for plants. Freshwater animals, freshwater fishes, for example, I mean, there's no ocean involved. So it means that there must have been continuity in the continents to actually make this possible. So this was one of the strongest bits of evidence that he could come up with, the fossil similarities. Now, the next problem, of course, was that people had talked about vertical movement. There was no horizontal movement on the Earth. How do we know that there was lateral movement? At that time itself, right, there was some indication that Wegener presented that he said that there were faults like the San Andreas fault. We know that there have been lateral movement of some time. We know that there is a huge movement of thousands of kilometers across faults like the San Andreas. Wegener had no idea how much movement there was, but there was. We know now that there is significant horizontal movement along these faults. And then he found very strong support in a South African geologist called Du Toit. And Du Toit was the person who actually presented a lot of additional geological evidence. Now, Du Toit's evidence was actually that, I mean, he also thought continents had moved, but rather than supporting the idea of Pangaea, he preferred to think that the continents were divided into two land masses rather than a single entity. Most importantly, however, Du Toit recognized something incredible. He realized that the present-day rift valleys, you've heard of the famed rift valleys of East Africa, along which all the great lakes are located, right? Lake Tanganyika, Lake Nyerere, Lake Victoria, all of these places, they are located along the East African Rift Valley. Not just that, he noticed these huge margins of what constitutes the Red Sea, the parts that separate Africa and Asia today. And of course, the Rhine-Graben in Europe. He actually said that these look like parts of the earth which had been together and are splitting apart. So he was the first one to identify on a large scale the evidence, geological evidence of rifting. He suggested that these actually represented early stages in the separation of continents. And this is something we think is correct even today. So you can think of the foresight of the man who had no idea, no access to all the information we have today. In 1937, right, he actually identified that these were the things that actually told us about splitting of continents. Indeed, he did some other things. I mean, we don't actually agree with all the matches he made, but he observed a belt of folded rocks, sedimentary rocks, which we refer to as the Cape Faults in South Africa. And he said that these actually, he continued them, he traced them into South America, and he suggested even into the eastern part of Australia. So it was one continuous belt. And he suggested that all of these rocks, you see, the rocks that make up these folds, right, these were all sedimentary rocks, which were deposited in a deep, narrow fissure in the Earth's crust, which was referred to at the time as a geosyncline. A geosyncline is a long, narrow fissure in the Earth's crust, right? So it's a depression. Wherever you have a depression in the Earth's crust, water will accumulate and there will be sedimentary rocks deposited in those fissures. So these long, narrow fissures were long referred to as geosynclines, and these are the ones which were crumpled up later to form mountains. So these crumpled mountains, which were continuous from South America and Eastern Australia, right, into South Africa, he called this the sunflower geosyncline. So this was one continuous belt, which are now distended. These are in separate continents now. But he actually managed to trace orogenic belts from one continent into the other. We don't necessarily agree with the sunflower geosyncline today, but we do know that there are other mountain belts which we can trace. For example, people like me are even today are engaged in trying to identify if mountain belts from India can be traced into the Antarctic, for instance. So, and these are the things that actually help us to trace what the continuity was between continents. So, Wegener, for his time, right, he actually compiled this. He tried to make up, right, the breakup of how the continents look like. So in the late Carboniferous time, around 300 million years ago, he suggested this to be the sort of configuration that the continents had. So South Africa was somewhere near the south, where the South Pole was at this particular time. So the Eocene, right, which is around 45 million years ago, by that time the breakup had begun. So things had begun to move apart, and the shape of the continents as we know it today had begun to appear. And by the early Pleistocene, which is just about 2 million years ago, right, the continents pretty much look like what they have today. Notice what India has been doing. So India itself was actually separated. According to him, it is separated in the Eocene, right? By this time, we also think that India had been together, but we think we have different ideas about how India actually moved now. Now, Wegener's famous theory was published in 1915 formally in this particular part, right? And this talks about the continents and the oceans. It's in German. So just to give you an idea of the sort of evidence he was talking about, this was the Permo-Carboniferous glaciation he talked about. And if you map them onto the present day Earth, you can actually draw a dashed line like this. And these are the areas where you have these evidence of glacial deposits. And these glacial deposits, geologists can actually make out which way the glaciers moved. And if you take these paleo movement directions of the glaciers, this is the directions in which the glaciers apparently spread. Now, the idea was that all of these areas which are disparate, these were all together near the South Pole. So if they were near the South Pole, the glaciers began spreading out from different sides. That's what you make out here. And that is the idea that Wegener actually proposed. And this is what Dutoit's discoveries also seem to survive. Now, a very, very famous geologist who's written a very famous book called The Principles of Physical Geology, Arthur Holmes, he actually drew this diagram in 1944 to indicate, right, what might indicate the extent of the Permo-Carboniferous glaciation, which indicates that these parts, which must have been connected by one landmass. However, even Wegener's theory had a problem. The problem was, now notice two words here, Sayal, sail over Sima. Now the whole idea that was Wegener had proposed essentially is something like this, that you had Sima and you had Sayal on top, and the Sayal was simply moving over Sima. Now, how would Sayal move over Sima? His idea, it was much like a boat moves through water. Now, Sayal as it moves would displace the Sima, just as the boat as it moves displaces water, and it would move ahead. This was his idea of how the continents would move over the oceans. Okay. By that time, even by that time, when Wegener proposed his theory, the problem was seismologists had produced evidence that told us that the seismic wave velocities of Sial are generally lower than those of Sima. Now, that is, the lower crust has higher seismic wave velocities than the upper part of the crust. Now, the seismic wave velocities are related to moduli of elasticity, and one of the most important moduli is the rigidity modulus, right, the shear modulus, which is a measure of how strong a material is. So, if a material has a greater rigidity, the seismic wave propagation velocity through that particular material is going to be higher. So, we know that Sial has a lower seismic wave velocity velocity with which seismic wave velocities are transmitted through it than Sima, which indicates that Sial is less rigid than Sima. In that case, unlike a boat and water, how could Sial plow through Sima? Right? That was what the problem is. Sial intrinsically is more rigid than the Sima. Then the problem was his equatorial bulge. He had thought that that little extra mass near the equator, that bulge, was responsible for dragging this continent. This extra gravitational force of this drag of this extra mass was simply not enough to create this driving force. So the driving force proposed by Wegener also was too small. So therefore now, the continental drift theory had a remarkable beginning. But if we try to summarize all the evidence, right, we'll see that there was a problem. So it was proposed independently by Taylor in 1908, Wegener in 1910. Taylor proposed two continental land masses, one near each pole, Laurasia, Gondwana land. Taylor proposed that the moon became the Earth's satellite in the Cretaceous period, and then the continents, right, were dragged towards the equator. This theory was discarded because the moon's gravitation was not that strong, and also you could not explain the existence of mountain belts older than the Cretaceous. So this was why Taylor's theory actually fell into disrepute. On the other hand, Wegener did not propose two continents, he proposed one, called Pangaea. And he presented a wealth of geological evidence in support of continental drift, and he was ably supported by the findings of Dutoit. Now, Wegener suggested that Sialic continents moved over Sematic oceans, and that the driving force was the Earth's equatorial bulge. So, the problems with Wegener's theory was that the driving force was not large enough, we knew that. More importantly, the seismologists proved that the mechanism he was suggesting, that the Sial was plowing through Sima as boats were moving through water, this did not work because we knew seismologically that the Sima was more rigid than the Sial. So the upper continental crust is less rigid than the lower continental crust. So it cannot plow its way through the lower continental crust. So therefore, both the mechanism and the driving force proposed by Wegener did not appear to be enough. So the final conclusion that happened by the end of the 1930s, now 1937 is when Dutoit's book came out. Even then, by that time, the theory of continental drift, although the observations were remarkable, it fell out of favor. And therefore, by the end of the 1930s, people didn't believe that it had taken place. But there was a catch. The catch was the observations, the theory could be disputed, the mechanism could be disputed. But the observations that Taylor, Wegener, and all the people before them had made, the match across continents, across the oceans, the matching of the coastlines, the similarity of sedimentary horizons, of fossils, land plants in these different places, evidence that continentals had moved over time because climate had changed. All of this was there. How did one explain that? So the theory may have fallen into disrepute, right? But the evidence was still there, and it was just in need of a new frame of reference. What frame of reference that was interrupted by the start of what is called the Second World War in 1939. What happened thereafter, right, we will discuss in the next lecture. So these are the set of references which refer to the old things that we get our knowledge from, and in the next lecture we'll try to discuss how this follows up. Thank you very much.